Okay, so we'll start the class. So I think so far we discussed about some introduction about this bolted joints. In the previous class, we have seen what are the advantages and disadvantages of these bolted joints. And after that, we discussed about what are different types of these bolted joints. Those are through bolt, cap or cap screws, and then studded connections. So then we'll move on to the next one, which is bolt of uniform strength. This is important in even in examination point of view also. You may get some 2 marks questions on this bolt of uniform strength. Like they will ask what is a bolt of uniform strength and explain something like that. You will get a question either for 2 marks or sometimes it may be 4 or 6 marks also. You will get the question. So now today we'll see what is that bolt of uniform strength. Then how we can create a bolt of having uniform strength. Bolt of uniform strength is nothing but the bolt which is having the strength is uniform throughout. That means the stress induced because of applied load, the stress induced in the bolt is same throughout the bolt or throughout the length of the bolt. Then we'll call it as a bolt of uniform strength. Anyway, we'll see that how we can make a bolt of having uniform strength. So for that, this is actually the general configuration or maybe the general structure of a bolt here, something like this. So we already seen the terminology of this bolt. So here in this, we'll call this one as a head. This is the head of the bolt. And then the portion, the cylindrical portion from this point to up to this point means, so where there are no threads. In this portion, there is no threading is there. So then this portion we'll call it as a shank. And then this remaining portion or the remaining length of the bolt is having some threads. So this portion we'll call it as a threaded portion. So here you have a threads. You can see this is the what you can say. So representation of the threads on a bolt. So here, whereas this is the shank portion through which you don't have any threads. Simply you have some cylindrical surface will be there without threads. We'll call that one as a shank. When you're making a connection with these bolted joints, we already discussed, this portion, the shank portion will be fitted into the hole of your connection. Then here you have a nut. So through nut you will make a connection here. So but here, okay, anyway, that we already discussed. But here, in the point of this bolt of uniform strength, what you need to look at it is, here the diameter of the shank is D. We'll call this one as a nominal diameter also. So D is the diameter of the shank. So now you can see that the diameter is throughout the length from this end to this end. It is same. Or we can call it as uniform. The diameter is uniform throughout the length of the bolt. So that is, it is same for the shank portion as well as threaded portion also diameter is same. But the problem here is, so we know in the threaded portion you have 2 diameters. One is called core diameter, another one or root diameter, another one we will call it as a nominal diameter or major diameter. So generally the load is taken by the core diameter. This core diameter is less than, you can see here, core means if I join the roots of the thread, so I'll get the core diameter. This is what you can call it as a core diameter, DC, denoted by DC. Anyway, we'll see these definitions later. This is D. If you compare this D to this DC is smaller than D. So then, if this bolt is subjected to, let us say, some tensile force P, here and this end, it is subjected to a tensile force P. Now, here the area is less, here the area is more. So therefore, we know stress is indirectly proportional to area. So if area is more, your stress is less. Area is less, your stress is more. So since here the diameter is more when compared to this location, what you can have is here you have a less stress value because the area diameter is more means area is more here. So in the shank portion you have less magnitude, stress of less magnitude when compared to the stress in the threaded portion. So that means, so here the stress is different, here the stress is different. So I cannot call a bolt which is subjected to different magnitude of stresses for the same load, we cannot call it as a uniform strength. As for the definition for a uniform strength of the bolt, the stress should be uniform throughout the length of the bolt. That means the stress should be same in the shank portion as well as in the threaded portion. So now if you take a bolt like this as it is, so we cannot call this one as a bolt of uniform strength because you have a variable stress magnitude. So in the shank portion you have one stress, in the threaded portion you have a stress having magnitude different from this. So we cannot call this one as a thread of or bolt of uniform strength. So now how I can make this one as a bolt having uniform strength? That is the next question. So for that we'll see some of the points how we can make the bolt as having uniform strength in these slides. So now here this figure we already discussed about this. Figure A shows that an ordinary bolt with usual shape, that like what I already told, generally the shape of the bolt will be like this only. The major diameter of the thread as well as the diameter of the shank is D. So that's what I already told to you. The core diameter of the thread is DC. When this bolt is subjected to tensile force, there are two distinct regions of stress. One is, okay, I'll arrange these things. The diameter of the threaded portion, that is DC, is less than the shank diameter. That's what we already discussed. The threaded portion is also subjected to the stress concentration. So this is also another point. That means whenever there is a geometric stress concentration or sharp edges are there, because of that you have a stress concentration. Since your thread is a sharp cylindrical edge groove, so therefore in the threaded region, in addition to the lesser diameter, you have stress concentration effect also. Therefore the stress induced in the threaded portion is more than the stress in the shank portion. So that's what I already told to you. Then the energy absorbed per unit volume of the bolt material is proportional to the square of the stress. So maybe this comes from your stress strain diagram. If you recall your stress strain diagram, in the stress strain diagram you might have studied about the resilience. Resilience is nothing but the amount of energy absorbed by the component when it is loaded up to the elastic limit. The same thing, if you write an expression for that, so your elastic limit, that is nothing but area under the stress strain curve up to elastic limit, you can call it as a resonance. If you write the expression for that, you will get in that expression it is a function of stress, and also not only simple function of stress, your resilience of the component or the energy absorbed for unit volume is function of square of the stress. If you recall your fundamentals of that stress resilience or energy absorbed because of applied load, you will get that function. So anyway, we'll take that here. So that is your energy absorbed is proportional to the square of the stress. So that means if stress is more, it is energy absorbed is also more. Stress is less, the energy absorbed also less. So here what happens here, hence large part of energy is absorbed by the threaded portion of the bolt. Why large part of the energy is absorbed by the threaded portion in the original bolt? What we seen here, because here you have a higher stress. So your energy absorbed is proportional to the square of the stress. Is proportional to square of the stress. Since here you have a lesser diameter, in addition to the lesser diameter, there is a stress concentration effect also there. If you compare sigma value at this location to this location, this is very, very high. So since it is very high, the energy absorbed is also going to be very high. Means if I calculate the total energy absorbed by this bolt, the threaded portion will calculate the maximum, or it will take the maximum amount of energy when compared to the remaining part of the bolt. So then what happens is, since only this portion, this is a you can say in the length of the bolt, it may be around 30% of the length of the bolt. So 30% of length of the bolt is taking around 70 to 80% of the energy. whereas remaining is taking only towards some 30%. So that means the energy is not distributed uniformly. So that means you don't have any uniform strength. So that is the problem with if you take a original or a general shape. So then what we need to do is, so then the second point here is the diameter of the shank is more than the core diameter of the threaded portion. This we already know. There is no stress concentration in the shank. Therefore, when the bolt is subjected to a tensile force, the stress in the shank portion is less than the stress in the threaded portion. This also we already know or discussed. Then the energy absorbed in the shank, which is proportional to the square of the stress, again is less than the energy absorbed by the threaded portion. That's what I already told to you. So then that means the less energy absorbed means it is the less having a capability of absorbing the shocks is very less. The shock absorbing capacity of bolt can be increased. So now if I want to increase the shock absorbing capacity for the bolt, then what we need to do is we need to make sure that by increasing the energy absorbing capacity of the shank, then you can make it is, it can take large amount of shocking loads or shock loads. So how I can make this one? So that means the shock absorbing capacity of bolt can be increased if the shank of a bolt is turned down to the diameter equal to the root diameter of the threads or even less. So meaning what? Meaning that here if it is possible to reduce the diameter of the shank. Originally, what is the condition here? In this figure, the diameter of the shank is more than the diameter of the core. So because of that, core is having the maximum stress and shank portion is having less stress. Now, if I am able to reduce this diameter such that the area of the shank is less than the area of the threaded portion or even less than that, then this shank can carry maximum amount of energy. That means the shank portion can absorb more amount of energy when compared to this. So for that, what you have to do is you need to reduce the size, or that is the diameter of the shank portion, not entire length of the bolt. So you are not going to change any diameter for the threaded portion. Only for the shank portion we need to reduce the diameter. By doing so, you will get, or you can make that this bolt can carry or can absorb maximum amount of energy through the shank portion. So then, if possible, we can make it. If the two diameters are equal, I can make it is uniform throughout also. So that's what here is stated in this slide. So in this case, the shank is subjected to higher stress. When it is going to subject to higher stress, since we are reducing the diameter. If you reduce the diameter, area will decrease. Area decreases means stress will increase. So that's what is stated here. So in this case, the shank is subjected to higher stress and hence absorbs greater portion of strain energy and relieves the threaded portion of high stress. So by doing this, you have two advantages are there. So one is shank portion is taking the more energy when compared to the threaded portion, means it is relieving from the high stress region also. So therefore, the resilience of the bolt can be increased by increasing its length also. This is another parameter. By increasing its length also, you can increase the resilience. The resilience is nothing but the amount of energy absorbed. So that means two options are there. One is either you can decrease the shank diameter or either you can increase the length of the bolt. So by doing so, you can do the both the things, but there is some limitation on the length of the bolt. You cannot have any length of bolt. So there is some restriction on the length of the bolt. So in that case, what we need to do is we need to go for a reduction of the diameter of shank portion. So by doing so, you can make that the shank portion can take a more amount of energy when compared to the threaded portion. So therefore, there are two methods for increasing the shock absorbing capacity of the bolts. That's it. One is reduce the shank diameter to core diameter of threads or even less. Other one is increase the length of the shank portion. So then the threaded portion of the bolt is the weakest one and maximum amount of elastic energy is absorbed in this region. Why it is the weakest one? Because its area is less and also there is a stress concentration. Because of that, more stress is concentrated on the threaded portion. That's why it is the weakest one. The ideal bolt will be one which is subjected to the same stress level at different cross sections in the bolt. It is called bolt of uniform strength. So therefore, this is the definition for a bolt of uniform strength. So what is the meaning of bolt of uniform strength? So in a bolt, if you take different cross sections, or if you identify the different sections in the bolt, at all the different sections, if the stress level is same, that means the magnitude of stress is same, then we'll call it as a bolt of uniform strength. So original usual shape of the bolt, if you look at the usual shape, we already seen that shank portion is having the less stress and bolted threaded region is having more stress. So that means in the usual shape, your bolt is not a uniform, having uniform strength. So that means we need to modify that original shape in order to call the same bolt as a bolt of uniform strength. So for that, these are the two things what we discussed. One is we need to reduce the shank diameter. The other way is there is another way of doing that also. In a bolt of uniform strength, the entire bolt is stressed to the same limiting value, thus resulting maximum energy absorption. So that means if your stress is uniform throughout, then the energy absorbed by the bolt is also maximum. Why? Because you are making that generally the shank portion is more when compared to the threaded portion, that is in point of length point of view. So if you make that the stress is same throughout, then the energy absorbed is also going to be maximum. Okay. Okay, so here to make that, that means in order to make the bolt taking the same strength or the magnitude of stress is same in both in the shank portion as well as in the threaded portion, there are two ways. How we can do that? There are two ways of reducing the cross-sectional area of the shank and convert an ordinary bolt into a bolt of uniform strength. One way is, like I already told you, this is the one way of doing that. That is, we'll reduce the diameter of the shank and we'll make the diameter of this shank portion is equal to the core diameter of this threaded portion. So that means here instead of D, we'll take this diameter also D. You can see that here the diameter of the shank portion is less than the diameter of the threaded portion. So this is one way of doing it. Or else the other way of is you can reduce the area. So if you reduce the cross-sectional area, obviously the stress will increase. So here we reduce the area by doing like this. Hey, Nura, Malita. ఇప్పుడే చెప్పింది మళ్ళీ అక్కడికి ఎందుకు వెళ్ళావు నువ్వు ఇక్కడ కూర్చో నేను వస్తారా కూర్చో So here we reduce the diameter of the core, so the diameter of the shank portion. So therefore here the stress is more. So then here you have a stress which is also equivalent to this. Then this will become a bolt of uniform strength. This is one way of doing it. Other way is to reduce the strength in a, okay, so if not you are not interested in reducing the diameter of this shank portion, what here it is done is a hole is created in the shank portion. See, you can see that here a hole is drilled into this thread in the shank portion up to this point. So then he has taken the diameter of the thread, the drilled hole is D1. So now from the analytical calculation, you can easily calculate what should be the diameter of the hole needed to be drilled into this shank portion. So for that, what you have to do is whatever may be the stress in the threaded portion, so the stress in this shank portion also equal to, you need to make them two are equal. So from that you can get how much diameter of the hole you need to drill in the shank portion. So from that you can easily calculate the D1. Once you know the D1, a hole of diameter D1 will be drilled into that bolt, so that the stress in the both the sections will be remain same. So then obviously it become a bolt of uniform strength. So that's what here written. One method is to reduce the diameter of the shank, that we already seen. The other method is the cross-sectional area of the shank is reduced by drilling a hole as illustrated in the figure C. So in the figure here, you can clearly see that here there is a hole which is drilled into this threaded portion. To find out the diameter of the drilled this D1, so the equation is like this. Both methods reduce the cross-sectional area of the shank and increase the stress and energy absorption capacity. Then in the first method, what we did is the diameter of shank is usually reduced to the core diameter. So that means we already know the diameter, how much you need to reduce. That is, you need to reduce the diameter to DC value, the diameter of the core. Therefore, the cross-sectional area of the shank is equal to the cross-sectional area of the threaded portion. When this bolt is subjected to tensile force, the stress in the shank and the stress in the threaded portion are equal because they are of same size. Then in the second method, the diameter of the hole, that is D1, is obtained by equating the cross-sectional area of the shank to that of threaded part. So therefore, this is the equation you need to consider. So this is the cross-sectional area of the shank portion, and this is the cross-sectional area of your threaded portion. So threaded portion is having a diameter DC, therefore 5/4 DC square is going to be its area. Here in the shank portion, the outer diameter is D, but we are drilling a hole of diameter small d1. So therefore, the net area should be the diameter of the shank, cross-sectional area of the shank minus the cross-sectional area of your hole. So now, if you're doing so, from that, if you simplify this, from this you'll get an expression for the d1. Your d1 is nothing but square root of d square minus dc square. So from this, you can estimate the d1 value. Once you estimate the d1 value, from that, you'll get the, once you got the d1 value, you can drill the hole of the size of d1 into that, so that your bolt will become a bolt of uniform strength, right? So, but here the thing is, you have a two ways. Either way, you can reduce the cross section. One way is either decreasing the diameter of the shank portion, or drilling a hole in the shank portion. Either way, you can reduce the cross section and you can make the stresses uniform throughout the bolt, or you can make the bolt or uniform strength. But if you consider practical case, so practically here, drilling a hole up to this much length in a bolt is going to be a difficult task. When compared to this, reducing the diameter is the easiest way. If you take the practical considerations, so reducing the diameter is going to be the easiest way when compared to drilling a hole in a bolt is going to be a somewhat difficult task. So therefore, if you consider the practical cases or practicality, the first option is going to be the preferable one. So that means just by reducing the shank portion to the diameter of the core or diameter of the core or root, you can make the bolt as having uniform strength. That's what here I written. Machining a long hole is difficult operation compared to turning down the shank diameter. So drilled holes results in stress concentration. There is another disadvantage also there. So if you drill a hole in the bolt, it will induce a stress concentration also. Therefore, it is not advisable. That means only we'll go for the first option. That is, therefore, a bolt with reduced shank diameter is preferred over a bolt with an axial hole. So that means instead of going for the second option in these two options, instead of going for the second option, so always the first one is preferred. That means in order to make any bolt having uniform strength, what you need to do is the diameter of the shank portion of the bolt should be equal to the diameter of the core. So that means whenever, if you calculate now onwards, whenever you calculate the area of the bolt, so you have to take only 5/4 DC square, not the nominal diameter, capital D. So small d. You cannot take the nominal diameter for the calculations. Since we are reducing the size of the bolt, you need to take it as diameter of the bolt as a DC only. Based on the DC only, you need to compute the tensile stress area. We'll call that one as tensile stress area. That means the area which is resisting this tensile force. Anyway, we'll see that definition and how we can calculate this tensile stress area also in the coming slides. So now, before going into that, we'll see some more definitions and then we'll enter into our actual analysis. When the bolt is subjected to some external load, what are the stresses? When the bolt is subjected to initial tightening, what are the stresses induced in the bolt? And similarly, when it is subjected to both initial tightening as well as external load, we'll call it as a combined loading. So in that case, how we can find the magnitude of stress values, or how we can design the bolt. So after that, we'll see eccentric loading also. So now in this, so before going into that, we know some terminology about these threads. So I think you might have familiar with all these things. Anyway, we're going to review them again. So here you can see that generally bolt and nut. We'll talk about bolt and nut only. So the difference between bolt and nut is, the major difference is, bolt will have external threads and nut will have internal threads. See, you can see the diagram wise, you can see that here, this is the diagram which is having external threads. So the designation is also different from external thread and internal thread. So that's why we need to look at into this terminology again. So this is the external thread. I can call it as a bolt or corresponding to the bolt, and this is having a internal threads. I can say this is corresponding to the nut. See, now if you see the terminology here small d is used for the bolt, d, small dp, small dc, like that. Small letters are used for the external threads. If we take internal thread like nut, you can see here the notations are capital D, capital DC. Similarly, you have a capital DP. So, but the names are same. So you can see that major diameter here also major diameter, here minor diameter, here minor diameter, pitch diameter and pitch diameter. So we are defining the same parameter, but the notation is different from for internal threads as well as for external threads. Internal threads will use capital letter, for external threads will use small letter. Okay, so now we'll see what are these definitions also. What is this major diameter? One by one, what is pitch diameter? What is minor diameter? Similarly, what is the pitch value? What is the threaded angle? And also similarly, what is a root and crest? Root is nothing but, say here, these two are also different. See, in case of internal thread, this is the external thread definitions for root and crest. Here, crest and root are different here. You can see that this is this point, highest point in the thread, we'll call it as a crest in case of external thread. ఏ బ్యాచ్ మీరు ల్యాబ్కి వెళ్ళాలా? అయిపోయింది ఇది, సరే వెళ్ళండి, మళ్ళీ వస్తారు కదా మధ్యాహ్నం. రైట్, 11:30, 11కి అయిపోయింది. ఓకే వెళ్ళండి. సో here we'll call this point, that is the highest point, we'll call it as a crest, and lowest point we'll call it as a root. Now if we come to this internal threads here, this is the what you can say, it is the lowest point, so therefore it is called root. Then this is the highest point in the thread, you can call it as a crest. But the diameter wise, so this is the largest diameter and this is the smallest diameter. So that is this we will call it as nominal diameter and this will call it as a core diameter. Anyway, we'll see that one by one. The definitions we'll see now. First definition, we'll take it as a major diameter. The major diameter is the diameter of an imaginary cylinder that bounds crest of external threads or the roots of internal thread. So that means if we take the cylindrical portion between two roots of a internal threads, that is, so this is the root and this is the root. So two sides you need to take this distance. You can see that here, you can see that the same thing is shown here. This we'll call it as a major diameter. So for internal thread, it is denoted by capital D. So that's what here it is shown. Similarly, if we consider the external thread, it is the imaginary cylinder that bounds the crest of an external threads. So now here you need to take, this is the crest for the external thread, this is the limit and this is the limit. So now the distance between these two lines, we'll call it as a major diameter. So this is the major diameter which is denoted by small d. Here it is capital D. So that is the first, and also sometimes we'll call this major diameter as a nominal diameter also. The major diameter is the largest diameter of the screw thread. It is also called the nominal diameter of the thread. So those who are already continuing, so A2 batch ఎవరైనా ఉంటే you can leave. A1 ఇప్పుడు A3 బ్యాచ్ ఒకటే ఉంది ఇక్కడ. సో ఇఫ్ యూ కంటిన్యూ ఉన్నా యూ అగైన్ రైట్ ఆన్ ద లాగ్ బుక్. కంటిన్యూ అయ్యే వాళ్ళు మళ్ళీ లాగ్ బుక్లో నెక్స్ట్ పేజ్లో పెట్టి మళ్ళీ రాయండి. సో యూ స్టార్ట్ ద 4th ఎక్స్పెరిమెంట్. సో 3rd కంప్లీట్ అయిందా? మరి ఎందుకు అటు ఇటు తిరుగుతా ఉన్నా నువ్వు? అరే ఒక నిమిషం 10 నిమిషాలు క్లాస్ అయిపోతే నేను వస్తాగా. సోషల్ డిస్టెన్స్ మెయింటైన్ చేయండి, దూరం కూర్చోండి అంటే అక్కడ పోయి కబుర్లు చెప్తాను. మీరు గొడవ చేస్తాను, నేను క్లాస్ చెప్తే ఉపయోగం ఉంది ఇక్కడ. అయిపోయింది నీది ఎక్స్పెరిమెంట్? మరి రాసావు అది? నేను అడిగేది ఏంటి, నువ్వు చెప్పేది ఏంటి? ఎందుకు అవ్వలేదు? రాయడం అయితే కదా అయిపోయినట్టు, చేయడం వరకు అయిపోతే అయిపోయినట్టేనా? వెళ్ళరా ఒక్క నిమిషం, 10 నిమిషాలు క్లాస్ అయిపోతా. జస్ట్ 10 minutesలో అయిపోతుంది, వచ్చేస్తా. నువ్వు ఏ బ్యాచ్? కూర్చో. సో అది సేవ్ చేసి పెట్టు, నీకు డౌట్ ఉంటే నెక్స్ట్ 4th ఎక్స్పెరిమెంట్ స్టార్ట్ చెయ్యి. వస్తా, మనం సేవ్ చేసి పెట్టు, నేను 4th స్టార్ట్ చెయ్యి, వస్తా. ఈ లోపల క్లాస్ అయిపోయినా వస్తాను. Right. The major diameter is the largest diameter of the screw thread. It is also called the nominal diameter of the thread. Okay. So this is the definition of major diameter. Then the other one is a minor diameter. So it is a reverse. See, if you look at the definitions for the major diameter and minor diameter, it is a reverse wave, reverse in case of for internal and external threads. You need to remember that point. The minor diameter is the diameter of an imaginary cylinder that bounds the roots of an external thread DC or the crest of an internal thread, so capital DC. The minor diameter is the smallest diameter in the screw thread. Whether it is internal thread or external thread, minor diameter is going to be the smallest one and the major diameter is going to be the largest one. So here the minor diameter is, it is in case of external threads, it is the cylindrical surface bounded by the roots of the threads. So this is the roots, line joining the roots, and these are the lines joining the roots. Then this diameter, you can see that this diameter is going to be from here to here. This is going to be the minor diameter. You can see that here shown is something like this here. This is the minor diameter denoted by small dc. Whereas if you come to this, now you have to take, these are the things. You have to take the crest now. So here these two cylindrical. Okay, anyway, here shown something here. Here shown it here. This to this. So this diameter we'll call it as minor diameter of internal thread, which is denoted by capital DC. Okay. So this is the definition for a minor diameter. Then, so like already told, root diameter is also called as core diameter, or minor diameter is, the other two names for the minor diameter is core diameter or root diameter. Both the names are same. Then the next definition is pitch diameter. So that is dp. Small dp for external thread and capital dp for internal thread. So what it is, the pitch diameter is the diameter of, ఎక్కడికి పోతాను అందరూ? బ్రేకా? ఎవడు చెప్పాడు బ్రేక్ అని? మళ్ళీ వెళ్తారు, మళ్ళీ శానిటైజర్. ఈ తలనొప్పి అనేది కూర్చొని చేయొచ్చు కదా, మధ్యలో పోయేతనేమన్నా వాష్రూమ్ అని చెప్పేసి మళ్ళీ బ్రేక్ ఏంటి నాకు అర్థం కాదు. అరగంటకు ఒకసారి వాష్రూమ్ కానీ వెళ్తూనే ఉన్నారు కదా, మళ్ళీ బ్రేక్ ఏంటి? నువ్వు వెళ్ళకుండా కంటిన్యూస్ కూర్చొని చేస్తే ఓకే, నీకు బ్రేక్ అంటే బ్రేక్ ఇచ్చేవాళ్ళు. 10 నిమిషాలకు ఒకసారి వాష్రూమ్ కానీ వెళ్తూనే ఉన్నావు, మళ్ళీ బ్రేక్ అంటే మళ్ళా the pitch diameter is the diameter of the imaginary cylinder, the surface of which would pass through the threads at such point as to make the width of the threads is equal to the width of the spaces cut by the surface of the cylinder. So that means here you can see that if you draw the imaginary cylinder for the pitch circle diameter here. If you draw like this is what we'll call it as, that if this diameter we'll call it as a pitch circle diameter. Here the basic difference is, here whatever may be the width here, that width is same. So the surface of which passes through the threads of such points to make that width of the threads equal to the width of the spaces cut by the surface of the cylinder. So this is the surface of the cylinder. So now here the width of the thread, if I take this width of the thread, this is the one and this is the one, this is equal to the space made here. So therefore if those two are equal, then that imaginary cylinder what having diameter, the diameter of that imaginary cylinder we call it as pitch circle diameter. Chandajay, we'll call it as pitch circle diameter. It is also called, the other name for this pitch circle diameter is effective diameter of the thread. Pitch diameter is denoted by dp if you use small letter for external threads and will use capital letters for internal threads. So then the next definition is pitch. Pitch is the మళ్ళా ఎక్కడికి పోతారు నువ్వు నాకు అర్థం కాదు. ఏంటి పిక్నిక్ వచ్చినా నువ్వు నాకు అర్థం కాదు. ఏ బ్యాచ్ నువ్వు? ఏది వెళ్తున్నావు వాష్రూమ్కి? ఎన్నిసార్లు వెళ్తావు వాష్రూమ్కి? మళ్ళీ ఒకసారి ఫోన్ కోసం, ఒకసారి వాష్రూమ్కి, ఇంకో అరగంట సేపు కూర్చొని తర్వాత తప్ప. Okay, anyway, we have two more definitions left out. We'll see those definitions and we'll stop the class now today. A lot of disturbance is there here. Okay, pitch. So pitch is the distance between two similar points on adjacent threads measured parallel to the axis of the thread. This is denoted by the letter P. So pitch is nothing but if you take any two successive points on the thread and if you measure the distance along the axis of the thread, we'll call it as a pitch. So that means either you can take two crests or two roots. Two successive, you need to take two successive points, two successive crests or two successive roots, then the distance along the axis of the thread will call it as a pitch value. Here you can see that here he has taken the two distance between the two successive crests. Similarly here also you can take the same thing here, two successive crests or successive roots also you can take. So that will call it as a pitch of the thread. So which is denoted, generally will use small p for the pitch of the thread. Then the next definition is lead of the thread. Lead is the distance that the nut moves parallel to the axis of the screw when the nut is given 1 ton. So that is nothing but, lead is nothing but the axial advancement of the nut for axial advancement for the bolt if you are for the screw. So if you give 1 revolution, then we'll call that one as a lead. So depending upon the number of starts in our thread, suppose if it is a single start thread, it will be moved by only 1 pitch length. If it is a double start or triple start or multi start, then depending upon that your lead value will also change. In case of single start thread, your lead is equal to pitch. In case of multi start threads, depending upon the number of starts, n, so your lead of the thread is nothing but n into p, where n is the number of starts. If it is double start, 2, triple start, 3, like that. Then the next definition is thread angle. Thread angle is the angle included between the sides of a thread measured in an axial plane. So now you can see here, this is the angle of the thread. So here we know different types of thread profiles will be there. For different types of thread profiles, the thread angle is also different. Like if I take ISO metric thread, the thread angle will be 60 degrees. If I take buttress thread, the angle may be 45 degrees. Like a Acme, so Acme thread you have a 27 degrees. Like you have different types of square thread, angle is 90 degrees. Like that you have different threads having different thread angles. So maybe that thread angle will depends upon the application. So thread angle is 60 degrees for isometric thread. So already tell isometric thread, we have an angle of 90 degrees. So then the last definition here it is tensile stress area. So here it has been observed that during testing of the threaded rods, that unthreaded rod means it is nothing but a shank portion having diameter equal to the mean of the pitch diameter and the minor diameter, mean of the pitch diameter and core diameter. That is nothing but mean means dp, pitch diameter is dp and core diameter is dc. Mean means dp plus dc divided by 2. That is nothing but the average of these two. So you can see that here from this you can see that mean of pitch diameter and mean of minor diameter. So this is your minor diameter and this is the pitch diameter. If you take the average of these two, then that is having the same strength thread as a threaded rod. So if you take average of these two dimensions and if you calculate the area based on that and if you compute the stress value, that is same as the tensile strength of the threaded rod. So that means if you want to compute the tensile stress area, you need to take this is the diameter. You need to consider this is the diameter for calculating the area. So we won't consider the major diameter, we won't consider the minor diameter. You need to take the average diameter of dp plus dc. Then based on that only you can calculate the tensile stress area. So that means 5 by 4 into, if d is diameter, the area is going to be 5 by 4 into d square, where this d which we are using for calculating the tensile stress area should be equal to dp plus dc by 2. So if you use that, you'll get the tensile stress area. So then this is the cross-sectional area. So the cross-sectional area of this unthreaded rod is called the tensile stress area. So here this is only the cross-sectional area of the unthreaded, that means shank portion. So our intention is we want to make the bolt as having uniform strength. So by doing so, we are reducing the nominal diameter of the shank portion. So such that we will make that dp plus dc by 2 is equal to the your area, cross-sectional area or diameter of the unthreaded portion or shank portion, so that your bolt will become having uniform strength. So therefore, based on this diameter only, we can calculate the tensile stress area. That means the area which is resisting your tensile load. So based on that only, we can compute the amount of tensile stress induced in the bolt also. Okay. So then this area is used for the purpose of calculating the tensile strength of the bolts. So always we'll use this tensile stress area. That means you need to calculate the area based on this diameter. That is only used to calculate the tensile strength of the bolt. So but for always it is difficult to compute what is dp, what is dc, then we need to find out the mean value of those two things. So this tensile stress area is provided in all standard data books. If you look at into any data book, so for all the data books, they will provide you this data. Instead of again and again for each bolt or each nut, if you want to calculate this dp plus dc by 2, all these things, and then you need to compute the tensile stress area. Instead of doing that, so already this data is provided in the data book just by calculating those values. Simply while solving the problems, what we need to do is instead of using this dp plus dc by 2 formula for calculating the diameter, straight away we'll pick the tensile stress area from the data book. Once you pick the tensile stress area, then your tensile load divided by tensile stress area is going to be the magnitude of the tensile stress induced in the bolt for the given load. So like that we'll calculate instead of using this calculation. But the concept of how we got this tensile stress area is this is the region. So this is the concept. Okay, right. I think okay. So still some more points are there need to be discussed, but I want to close at this point today. Maybe my laptop power is also not there; it is also going down. So anyway, I'll stop at this point today. We'll continue this in the next class. Okay, you just I think I already posted the attendance sheet. You respond to the attendance sheet and then you can leave the class.